So, in the last lecture we have discussed the cuts related to the real numbers, and in fact we have also given the idea of the Dedekind's theorem, and that theorem says, if you remember that if Dedekind, if you just go through the recapitulate our thing, what is the Dedekind's theorem is that if the system of real number is given, then we can divide this system into the two classes, lower class and the upper class, such that each class will contain at least one number. And second part is every number belonging to one class or the other. So, these classes will be non-empty, and the real number will belongs to either one class or the other class. And third point is that every number in the lower class is less than the every member of the upper class. Then this cut, this section we denoted by alpha, and we say alpha represents the real number. The alpha may or may not belongs to the, if it a rational number, it will belongs to one of the class either L or R, and if it is a irrational number, then it may not be belongs to the, it will not belongs to the class L or R. Okay. This can also be justified, this theorem results can also be justified as follows. Suppose we have the cut alpha is a real number, which bifurcate the entire all the real numbers into two classes, lower class and the upper class. Okay. Now, in this case, suppose we construct the L dash and R dash as the set of rational numbers, set of all rational numbers, rationals, set of all rationals which is in the class L, formed to L, and set of all rational which are in the upper class R, rational in L, set of all rational in the upper class R, and let us note these value by R. Okay. So, they will form the two classes, every rational number will be in one of the class either L dash or R dash, and number will be. Now, there are three possibility. One is the case 1, if this, because L dash and R dash, these are collection of the rational point. So, L dash may have the greatest number, get a number, R dash may not have any least number. Second case, when L dash does not have a greatest number, R dash has a least number, and third case when none of them is having. Okay. So, first case, if the class L dash, the class L dash has a greatest number, say L, number L, and the class R dash has no least number. No least number. Okay. Then every real number A, then every real number A which is less than L, which is less than L, it is number less than L, belongs to the class L. Belongs to the class. Why? Because this L dash has a greatest number L. So, any rational number which are less than L must be the point in this, and between any two rational number there are the further rational number. Similarly, between two real number we will show that there are infinite number of real numbers. So, if any number A, any real number A, whether it is rational or irrational, if it is less than L, it means it must be the class in L dash, if it is rational, is it not? Otherwise, it will be the class in L, because L is the lower class contains all the rational and irrational numbers. So, basically any number A which is less than L must be the point in L. Okay. So, that is one point, and similarly every real number B, similarly every real number v, every number v greater than L, greater than L, every number v greater than L belongs to class R. Again the same thing. Okay. Any number b real number, if it is a rational point, then it will, because it is greater than L, it must be in R dash. So, obviously, it will be in R. So, if it is a not rational, then we can choose all the points, because it is the lowest, all the number which are greater than will be come over here. Okay. So, that will be fine in this class, and every real number will be greater than this one. This is evident V is rational. Okay. So, thus L is a number alpha for this. So, what is so here? So, L correspond to our alpha, is it not? In this case, the alpha real number basically is nothing but L. Clear? Similarly, in the second case, if the class L dash has no greatest number, but R dash has least number, say small r, then the same repetition case will be there, and here in the same case same alpha becomes R. In the third case, the class L dash has no greatest number, and the class R dash has no least number. Then basically this section will define a rational point. Then the section, is it okay? Then the section L dash R dash, this defines an irrational number beta. Okay. Now, our aim is that this all the real number will be either in L or in R. So, all the rational number, which are less than beta, all the rational number less than beta belongs to L, and every rational number greater than beta belongs to R. Why? Why it so? Because this is our beta, here this L, this is R. I am choosing L dash and R dash, and beta I am taking such a thing where L dash is neither having the greatest number, R dash does not have the least number. So, it will the section represented by beta. Now, we claim this beta is basically the number, real number corresponding to our cut LR. Then, if we choose any number less than beta, then that number, if it is rational, it will be the point in L dash. So, it will be the point in L. So, all the rational which are less than beta must be the in L. Suppose I take a irrational point, then what happens, the point which are say any point beta dash which is less than beta. In between beta and beta dash, there are infinitely many irrational points. So, those points are in the L dash, hence it is in L. So, beta dash has to be in L. So, therefore, all such number rational number greater than less than beta must be in L, or rational number which are greater than beta must be in this. Okay. So, this is one can. Similarly, we can prove for the irrational case. Similarly, if every irrational number irrational number beta dash less than beta belongs to L, while the irrational number greater than beta belongs to R. And the reason is, I have just justified the reason, because there are rational number in between beta dash and beta which are in L dash. So, it is in L, therefore, this way similarly other. So, this way we can say that if we take a aggregate of the real number or set of all real numbers, we can always divide into two classes, where both the class will be non-empty and elements either lower class will have the largest element, upper class will not have a least element, and vice versa, and every element of the lower class is less than the every member of this, and the alpha correspond to this section. So, if it is rational, it will belongs to one of the class. If it is irrational, then it will not belongs to any of the class. So, this is the way the Dedekind had introduced the concept. Okay. Here in this process, though we have not justified, but what we have assumed it, between any two real number there are infinite number of reals also, is it not? That is the way justify. Between any two rational number, we can justify it as a rational number. What about the irrational number? If there are two irrational number, can you say again there are the infinite number of the rational and irrational number in between it? The justification is follow. So, we can go through the some properties, the properties of real number. The first property is, between any two real numbers, there are an infinite number of rational numbers. Between any two real numbers, there are an infinite number of rational numbers. Let us see how. Suppose we have the two numbers, one is alpha 1, another one is alpha 2. So, let alpha 1 and alpha 2 be any two real number such that alpha 1 is less than alpha 2. So, alpha 1 will correspond to the section L 1 R 1. Okay. So, alpha 1 will correspond to the section L 1 R 1, alpha 2 will correspond to the section L 2 R 2. Is it not clear? Now, the position is like this is alpha 1, here is alpha 2. This corresponds to section L 1 R 1, this corresponds to section L 2 R 2. So, every element of L 1 is basically element of L 2. Every number which belongs to L 1 is also the in L 2. is not, because alpha 1 is less than alpha 2, but all the numbers of R 1 is not in R 2. It means, some of the elements of R 1 must be in L 2, is it not. So, because of this, so we can say that every member, since alpha 1 is less than alpha 2. So, this implies that every member of L 1, every member of L 1 belongs to L 2, every member of L 1 belongs to, but every member of R 1 R 1 does not belong to R 2, because these are the points which are left out, is it not? These are the points which does not belongs to R 2 then, okay. But they are in R L 2, but they are in L 2 which belongs with the. So, these members, these members of R 1 belong to L 2, is it okay? So, now if we pick up any two elements from L 1 and L 2, okay. So, let A 1 belongs to L 1 and A 2 is in R 1, but not in L 1, not in L 1. It means, I am taking here somewhere, is it not, this point, it is in here, this is the point A 2, oh sorry, yes, this is the point A 2, which is clearly A 2 is in L 2, or A 2 belongs to L 2, such that, let us take this, A 1 is in alpha 1, here is A 1, A 2 I am taking in L 2, which is in R 1, but not in R 2. So, those points. So, A 2 minus A 1, or so clearly A 1 is less than A 2, okay. This A 1 is less than A 2, but what is the A 1? A 1 and A 2 are the point in the same class, and class L 2, all the elements which are less than alpha 2 must be the point in L 2, and there are infinitely many points. If I choose between A 1 and A 2, there are many points which we can introduce in between A 1 and A 2, which are in less than alpha 2. So, it is again in this. Okay. So, what we can between A 1 and A 2, if A 1 and A 2 are rational, then we can introduce many infinite number of. So, infinite rational points can be introduced in between A 1 and A 2, which lie in L 2. Is it okay or not? Which lie in L 2.
A 1 plus A 2 by 2 in this way.
Huh?
A 1 plus A 2 by 2.
Yes, yeah, like this way. So, we are infinite. It means between any two real number, but A 1 A 2 is satisfying this criteria, alpha 1 less than alpha this, alpha 1 is less than A 1. No, sorry, I am yes, no, A 1 is less than alpha 1, A 1 is less than alpha 1. So, it is alpha 1, A 1 less than alpha 1, A 2 less than alpha 2. Okay. Now, if we take A 1 here, say here I take A 1 dash, then similarly, if I take alpha 1 less than A 1 dash, which is less than A 2, which is less than alpha 2. So, in between alpha 1 alpha 2, there are infinitely many rational number can be introduced, and that is what he says, that between any two real numbers there are infinite number of rational points. Okay. So, again I believe what I did, suppose you choose the two real number alpha 1 alpha 2, then ordering relation is can be defined. So, alpha 1 is suppose less than alpha 2, it means you are having a cut of this type. Okay. This is alpha 1, here is alpha 2. What we want, in between alpha 1 alpha 2 there are infinite number of rational numbers. Okay. So, what I am taking is I am picking up two rational number, one is a 1 dash, another one a 2. A 1 dash is a point in R 1, but not in L 1, a 2 dash is a point in L 2. So, obviously, a 1 dash and a 2 we can again order them, let a 1 dash is less than a 2. A 1 dash and a 2 are rational number. So, in between these two rational number we can introduce infinite number of rational point again. Therefore, in between alpha 1 and alpha 2 we can introduce infinite number of rational points, that is what it says. Okay. So, this is second case is, second property is between any two real number between any two real numbers there are an infinite number of irrational numbers. Okay. Now, proof is, suppose let alpha 1 and alpha 2 be any two real number. Real numbers such that alpha 1 is less than alpha 2. Now, in the previous property, between any two real number we can introduce rational points. So, let a 1 and a 2 with the two rational number, two rational numbers lying between alpha 1 and alpha 2 such that alpha 1 is less than a 1 is less than a 2 less than alpha 3 alpha 2 sorry less than alpha 2. Okay. Because alpha 1 alpha 2 real, so in between we can introduce the rational. Now, what we want to show that in between these rational number are there. So, let beta be a rational number, let beta be a rational number, let beta be a rational number, irrational number, beta be a irrational number lying, let beta be a rational. If it lies in between, if it lies in between a 1 and a 2, then our problem is solved. Then obviously, it will lie between, it will lie in between alpha 1 and alpha 2. Okay. Suppose it is not, suppose beta does not lie, or you can write there exists a rational number beta. Suppose beta does not lie in between a 1 and a 2. Suppose beta does not lie in between, then we can choose a 1 and a 2, then find the two rational number b 1 and b 2 such that beta lies between b 1 and b 2 and b 1 minus B 2 or B 2 minus B 1 is less than A 2 minus A 1. Let us see how it what we did. Suppose we have this alpha 1, here we have alpha 2. In between alpha 1 alpha 2, I have taken the point A 1 and here is say B A 2. Okay. There are infinite many points alpha 1 A 1 A 2. Now, in between A 1 A 2, there are the rational number irrational number some. So, suppose beta is a point irrational number lying between this, then obviously, it will lie between this alpha. If it does not lie, then it will lie outside of it something. So, suppose beta corresponding to this beta, we can identify the rational number B 1 B 2 such that beta lies with B 1 B 2, but the difference between beta B 2 minus B 1 is less than this. Okay? Means this difference A 2 minus A 1 is less than B 2 minus B 1. Here is something B 1 B 2 like this, okay, whose difference is less than this difference. Then the consider then the number beta plus A 1 minus B 1. This number is a irrational number lying between and will lie and lies between A 1 and between A 1 and A 2. Why? Suppose beta is does not lie between A 1 and A 2, then I can choose the two rational number which can enclose the beta 1 beta 2 sorry beta B 1 B 2. So, construct a number beta plus A 1 minus B 1. What I claim, this is a irrational number. Irrational is obviously true because beta is irrational. So, any number say under root 2 is irrational, then 2 plus root 2 will also be irrational. So, this is irrational, there is no problem, but what he says it lies between A 1 and A 2. Why? Because the beta plus A 1 minus B 1, this number when you write okay, when you write beta plus A 1 minus B 1, this can be written as A 1 plus beta minus B 1, but beta I am assuming lying between B 1 and B 2. So, beta minus B 1 will be positive. So, this entire thing will be greater than A 1, but this is positive. So, any number positive number added, this quantity will be bigger than this. So, we are getting this number will lie will be greater than A 1. Similarly, beta plus A 1 minus B 1. Now, A 1 minus B 1, from here we can write this, since we have assumed B 2 minus B 1 is less than A 2 minus A 1, this we have assumed. So, what happen is when you take this side B 2 minus A 2 is less than okay, A 1 minus okay, B 2 minus A 2 is less than minus A 1 plus B 1, is it not, or B 1 minus A 1. So, this A 1 minus B 1 is less than A 1 minus B 1, if you transfer here is less than A 2 minus B 2. So, if I take this is strictly less than beta plus A 2 minus B 2, and again this is A 2 plus minus times B 2 minus beta, but beta lies between what? Beta lies between B 1 and B 2. So, B 2 is greater than beta. So, B 2 minus beta is positive. You are subtracting a positive quantity from A 2. So, will it not be less than A 2? So, this number lies between A 2 and A 1. So, we have constructed if a irrational number does not lie between A 1 and A 2, then we can rewrite this number in such a way, so that this new number irrational number will lie between A 1 and A 2. It means, between any two real number we can introduce the irrational number, and there are infinite numbers. Okay. So, these are the two property which enjoyed by this. Okay. Now, we have seen that apart from the rational, there are irrational number like under root 2, under root 3, etc. But whether these are the only irrational number, the question arises. Can we say there are some other irrational number other than these surds? These are called the surds. Say irrational numbers under root 2, under root 3 and so on so forth, or maybe 3 to the power cube root of 3 like this. These are all irrational numbers. And not only this, if I take 2 plus root 2, it will be a irrational number, or 2 plus root 2 and then root 2. This is also a irrational number, and like this way we can go ahead further. Okay. So, what it says is there are so many irrational numbers. Now, if we look these numbers, suppose I take root 3 or the number like this, suppose 4 plus root 15 cube root of 3 plus cube root of 4 minus root 15. Suppose I take this number. Okay. So, if I take the number, we can write it, suppose this is x, then if I simplify this number, then we can say that this comes out to be, this is equivalent to x cube equal to 3 x plus 8. X cube is 3 x plus 8. Why? Because if you take the x cube, then what happen is, because x cube means a plus b whole cube is a cube plus b cube plus 3 times a square into b plus 3 times a into b square. Okay. This is the expression for this x cube. Now, this gets cancelled. So, what we get 8 plus 3. Now, this will be equal to what? 4 plus root 15 and then a plus b into a minus b, a square minus b square. So, 16 minus 15 is 1. So, nothing. Then here is plus 3 4 minus root 15. Is it okay? Just I am combining this a plus b, a minus b, a square minus. So, you are getting this, but again if you take 3 outside, then what you get? Is it not the same as x cube plus 3 x? This is cube root. Yes. So, what you are getting is a cube plus b. Here something mistake I did it. What is this expression? A plus b cube means a cube 3 will be out, b cube 3 will be out, then square of this. So, 2 by 3, is it not? Into 1/3, then again 1/3 into 2 by 3. Is it correct? Because a square means what? It is a cube root, power 1 by 3. So, square means 2 by 3, multiply this 1 by 3. So, when you take this outside, this becomes the what? Is 1/3. If you take outside 1/3. So, finally, what you are getting is square of this 1/3 and 1/3. So, 1/3 is outside, 1/3 is outside. Okay? And then now, this is x. So, it becomes the 8 plus 3 x. Is it okay? So, we get this one. No, it is not clear. By this is the formula is a plus b cube is a cube plus b cube plus 3 a square b plus 3 a b square. This is the formula. So, using this formula,
We can take 3 a b common, 3 a b into a plus b, and a plus b is x here.
This okay. So, you can get it. Yes, a plus b is x. Yeah, that is also we can get. Clear? So, you get it.
Is equal to 1.
No, a b here will not be 1 because its power 1 by 3 is there. Na? So, how can you say it is 1?
Okay.
You just open it and take here what I am doing is 4 plus 1 by power 2 by 3 is there. I can write 1 by 3 into 1 by 3. 4 plus root 5 power 1 by 3 multiply by 4 plus root 5 power 1 by 3 and then 1 by 3 combine 4 minus. So, that becomes 1. So, only this term is there. Similarly, this. Okay. So, that is one. So, what it says is this one. Similarly, if we take this number, this is say x, one can easily write it this x cube equal to 3. Now, let us see the converse part. Suppose an expression is given x cube plus 3x plus 8 and it is asked to find the x. If it is a equation, algebraic equation of degree 1, we can write it. Algebraic equation 2, we can also find the x explicitly. Even x equal to 3, power is 3, we can find the expression like, but it is comfort. But when the power, when the algebraic equation is having the degree more than 3, in fact, more than 3 or 4, 5 etcetera, it is very difficult to write the x in the form of the surds. Though theoretically it must come because it is a solution of the algebraic equation. Clear? So, what we conclude is that when we have a general algebraic equation with the integral coefficients, then the solution of these algebraic equation will give either a rational number or maybe a irrational number. So, always you find the roots of this algebraic equation will be rational or irrational. Sometimes it is possible to find the explicit form of the irrational number depending on the degree of the polynomial. Is it a polynomial in x? If its degree is comfortable, we can identify x as insult. If its degree is higher, we cannot write, but theoretically it should come. So, what we conclude is that the solution of all algebraic equation will always give a real number, that is irrational number or rational number, both. Is it clear? Why rational number? Suppose I take just for x equal to p by q. This is rational point. Is it not a equation q x minus p equal to 0? It is not an algebraic equation of degree 1. So, it means the solution of algebraic equation may be rational also, but if we take the equation like x square plus 1 equal to 0 or x square plus 4 equal to 0, something like that, then we are getting something irrational points or minus 4 you can say, because otherwise I will take the lead complex. So, if I get this one, then you are getting x equal to plus minus 2, but if I get x square minus 3 equal to 0, you get a irrational point. So, in general we can say that the roots of an algebraic equation of the form a naught x to the power n a 1 x n minus 1 plus a n equal to 0, where a naught, a 1, a 2, a n are integers. Integers are called algebraic number. Algebraic numbers, okay, are called the algebraic number, and these algebraic numbers are either rational numbers or so basically they are real, that is reals. The solution of the algebraic equation will give a real number. Okay. Is it clear? But just by taking the solution of the algebraic equation, we are getting a irrational number also. Will it exhaust the entire irrational points? Means these are the only irrational number which can obtained? The answer is no. It is not only the solution of the algebraic equation only can give the irrational point, and the irrational set of irrational number is complete, is not true. There are some other irrational number which are not the solution of an algebraic equation. So, others number, the numbers which are not the solution, which are not the solution of an algebraic number, of an algebraic of an equation 1, of an algebraic equation 1 are known as transcendental function, transcendental number, TRN is transcendental numbers, transcendental numbers. Okay. For example, our pi is a transcendental number. It is not a solution for any algebraic equation. What is pi? Is basically the circumference of a unit circle. If you take a unit circle centered at 0 with a radius say 1, then what is the circumference? 2 pi r, is it not? That if r becomes 1, r becomes 1, then the diameter of this diameter is 2 pi, 2 pi diameter. So, that diameter 2 pi will give the pi. Okay? So, basically the pi is a transcendental number. Okay? Then there is another one E, that also a number. What is the E? Is a base of Napoleonian logarithmic base of the log, natural log with base E. So, this E is a transcendental number, is not a. Then these numbers similarly e to the power x, all these numbers are irrational number. Are irrational numbers. In fact, e to the power x, tan inverse x, e to tan inverse x, log x to the base e, etcetera, these are all irrational number. Irrational numbers for rational values, of x. Tan inverse x is a irrational number when x is rational. E to the power x is irrational when x is rational. Log of x is irrational like this. So, the set of collection of the irrational number is a very big set, bigger set, and here we can get clear. So, this one. Now, there is a result. The result says is the square root of any positive real number which is not perfect gives irrational point. Give irrational point. If a is a positive real number, but it is not a perfect. Perfect means that a cannot be a square of a is not an say it cannot be expressed as a square of some integers, it is not perfect. Okay? The square root does not come out to be an integer. So, if it is not a perfect, then its square root must be a irrational point. The proof is very simple. In case of root 2, we have already shown. Suppose I take a general one, let a real number a, let a equal to m by n, which is rational point, rational number, positive rational number, which is not perfect, not perfect, okay? It is not perfect, but we want to show that the square root of this will not be a irrational point. So, let square root of this is a rational number, suppose p by q, where p and q does not have any common factor. Common factor. In fact, it is the least. Similarly, m n, we assume m and n does not have any common factor. This is also in the least form. So, both are in least form. Okay. Now, let us see, under root m by n is p by q. Okay. So, we get from here is m square into q, sorry, m into q square equal to n into p square, let it be 1. Now, when we take this one, q square, m into q square is n into p square. So, we can say that m divides p square, because m cannot divide n, because m n are in the lowest form, m and n is given in the lowest form.
They do not have any
Because m by n is in lowest form, they do not have any common factor. So, only possibility that m must have a common factor with p square, is it not? So, from here m must have common factor with p square. Similarly, so m can be written as lambda times of p square, is it not? Once it is a common factor means it. Similarly, n must have a common factor with q square. So, n must be equal to lambda into q square, is it not? But this lambda m and n are in the lowest form. So, lambda must be 1, because m and n does not have any common factor, it is in the lowest form. M by n we are assuming in the lowest form, this is the lowest form. A rational number, when you are writing rational number, say 1 by 2 or say 3 by 4, it is in the lowest form. Suppose it is 6 by 8, we do not take it as a 6 by 8, what we do, we put it in the lowest form, is it not? So, that there is no common factor in it between. So, m by n is a only common factor is 1, that is all. So, at the most lambda will be 1. So, when lambda is 1, since m by n is in lowest form, so lambda must be 1. Therefore, what does imply? Therefore, m is equal to p square and n is equal to q square. Okay. What do you mean by this? What do you mean by this? It means m by n is nothing but the p square by q square. So, if I take a square root, it comes out to be p by q. It means m must be the square of some number, m must be a perfect square, n must be a perfect square. Clear? So, a contradiction. So, a contradiction. So, this shows there implies m and n are perfect squares, which is a contradiction. Okay. Is it okay or not? So, therefore, m by n, square root of m by n is irrational. Okay. Now, suppose we have the any number of the real number, rational number is perfect square. Okay. Positive integer. Second case is, let m be a positive integer. Positive integer which is not perfect. Okay. We wanted to show that this is, it is required to prove is that square root of m is an irrational point. Okay. Suppose it is not true. Suppose it is not true. So, let p by q be the number. So, suppose p by q is a fraction, in its lowest form, whose square is m. We are assuming this is a rational number and p by q and in the square is this. Okay. Now, since p by q is a rational number, so there are the 2 point lambda and lambda plus 1 which can encircle this p by q, p by q will lie between 2 integer, because any rational number you choose, you can always identify the 2 consecutive integer in between the rational number lies. So, is it not? So, we get there exists. So, suppose that, suppose lambda and lambda plus 1 are the 2 integers, between which p by q lies. It means lambda. So, what we get is p by q lie. Okay. So, lambda plus 1. So, we get from here is, so we get lambda is less than p by q less than lambda plus 1. This implies that q into lambda into q is less than p less than lambda plus 1 p. Let it be 2. Okay. Also, p by q is equal to what? Under root m. So, this shows that p square minus m q square is 0, like 3. If with the help of this, if we write this equation identity, consider the identity, this just you verify. Okay. M q minus lambda p square minus m p minus lambda q square, you will see the value of this will come out to be the lambda square minus m, or we can rewrite this expression into this form which is 0. This expression m q minus lambda p whole square minus m times p minus lambda q whole square, I just open it and rearrange in this form, then you are getting this expression, but lambda square is m, because this is p square minus m q square is 0. So, this part is 0 means total thing is 0. So, total thing is 0 means this is also 0. So, from here we can write m h m q minus lambda p whole square divided by p minus lambda q whole square, is it not? P minus lambda q whole square m. So, what you are getting is the m, this is also a number, but what is the denominator? Yes, I think is m. Yeah, the denominator is p minus lambda q, while the m earlier was this p by q. I think here something lambda p, m q minus lambda q is another fraction square. So, denominator of this fraction is less than q. Why less than q? This will be Yes. So, when you write here p minus lambda is what? P minus यहाँ पे this will come from here. Yeah, you take it this one. P minus lambda q is positive. Okay. P minus lambda q is positive. It means this whole thing is less than p. This is whole thing is less than p, because p minus lambda q is less than p. Similarly, here we can say, so we are getting m into another form rational, where the denominator changes. Denominator changes to a lower form, but m is in the lowest form. So, it is contradiction. Okay. So, this leads the. Okay, I think this I will continue next time. Okay, thank you. Okay. Clear? This is.